how many times we need to apply the chain rule. So we need to look at the level of embedded functions here. So we'll start from the outside. So there's a log function on the outside. So that's one layer. Inside that log function, there is a squared function. Okay, and it's not the sine function, but it's a squared function. It's the next layer function. So inside the squared is our sine function. Just getting a different color here. So the inside function here is the sine. Okay, so there's our sine function. Oops, I think I missed one here. Inside the sine function, there is a cube function. Okay, so maybe I'll do this in orange. There's a cube function inside the sine, and then inside the cube is a times 4 function. Okay, so I'm just going to write this as times 4. Okay, so we have 1, 2, 3, 4, 5 levels of functions here that we have to differentiate. So when we differentiate this, we end up with, we're going to go from outside in, y prime is equal to 1 over sine squared 4x minus 1 cubed, and I'm going to put some extra brackets in here, cubed. Okay, so that's the first part. That's the first layer derivative. The next layer derivative is going to be the squared, so it becomes times 2 sine 4x minus 1 cubed. Okay, so there's the derivative of the squared. Now we differentiate the sine into cos. We end up with cosine 4x minus 1 cubed. Okay, so there's our next layer. After this, we have to differentiate the cube, so it becomes times 3 4x minus 1 squared. Then lastly, we're going to differentiate the times 4, so we end up with times 4 there. Okay, so there's my derivative. I have 1, 2, 3, 4, 5 kind of layers in here, and I'm working outside in as I differentiate this. Lastly, here we have matching graphs with their derivatives. So the main ideas for matching graphs with their derivatives is some key points. Okay, one of them is we want to know where zeros of the derivative are the min and max points. So zeros relate to min and max. Okay, so wherever we have a 0 or a min and max is vice versa, right? It goes both ways. Okay, so the min and max of the y function. Okay, so this is what I'm going to look for first. So this is this is a graph, and this is the derivative functions here. So these are my derivatives. So when I have a 0, and I look at the first one here, I have a 0 here. Okay, I'm looking for where it's a min or a max. So in this case here, this min here or this max here could match that 0 here. Okay, so we also want to look for where the slopes are positive, so where y prime is positive or negative, and that relates to slope positive or negative, okay, on the y graph. So in this case here we have negative slope, and this is a different color. We have negative slope here in this section, and here we have negative slope. On this section here we have positive slope, and here we have positive slope. So these two seem to coincide with each other. That does not happen here, since it's going negative to positive, negative to positive. So this is, although the zeros match here, the 0 here matches a max here, the slopes do not match. The positive and negativity of the slopes do not match. So these two must go together. The other thing that we can look at is this idea of this max on a derivative represents an inflection or change in concavity on the y. So here we have an inflection. So there's an inflection here. We go from positive concavity to negative concavity. And we have inflections kind of, well, we kind of rule that one out, but there is an inflection here and here on this graph. Well, clearly the inflection only matches here. Okay, so we can see by just inflection that these two graphs are going to match. We can also check their zeros. There's my 0 here matches min here, max there. Our negative slope, negative, positive slope through here, yeah, it's a positive slope through there, negative values through here, negative y coordinates here, give us negative slopes through there. So those definitely match. So we can do the same thing here. We can check the min and max. That these two should reflect inflection points. So in this case here, it looks like D, those min and max relate to the two inflection points here. We can check the 0. 0 should relate to min or max. Yeah, there's a min or max here. There's another 0 here and here. Yeah, they relate to these zeros or min and maxes there and there. So clearly these two match. Okay. And lastly here, this one is, by default we know that these two match, but we can just also analyze this. These are discrete changes in slope. Well, here we have discrete changes in slope. Okay, so this must be, by that feature, these could be the same. Here we have positive slope, yeah, positive slope, negative slope. It looks like these slopes are equivalent but negative, and it looks like we have positive, negative, positive y, and this is exactly the same negative y. And then we have the exact same slope here, the parallel slopes, so it should give us the same y coordinate here and here. So these two graphs then are matching graphs. And there's not the key feature really that is most telling in this case, I think, is the fact that this is discrete slope, this is discrete slope. So there's some key ideas here that we can use. We can use these main ideas to be able to analyze the derivatives and their graphs of y. There's a fourth thing in here that I'm going to add in, and it's the polynomials. Okay, so the polynomials relationship that we know that if we differentiate, we should have 1 degree smaller. So if this is my derivative, it's this is a little bit harder because it's not really a polynomial graph, but I can see I have 1, 2, 3 kind of arms there. I should have, you know, 4 arms here, 1, 2, 3, and it's going to probably go down there. So we can kind of relate it in terms of the shape. So here we have a 4th degree should relate to a 3rd degree. 3rd degree should relate to a 2nd degree function. So there is also this polynomial relationship that we can use to help connect graphs to each other.